Section 3.3 has a lot in common with Section 3.2. It talks about increasing and decreasing functions. And an increasing function, I mean, you guys know what it is when you see it. There's lots of things like that in your life where you say, I can't define it, but I know what it is when I see it. This is an actual definition of it. An increasing function is a function where when x1 is less than x2, f of x1 is less than f of x2. I'm going to draw you a picture. And then a decreasing function shows it the opposite. x1 is less than x2 implies that f of x1 is greater than x2. So all I've got to do in terms of my x-axis is I'm talking about having x1 before x2, just the ordering along the x-axis. And then in terms of the y values here, what we're saying on an increasing function is that this y value is less than this one. And something happens in between. Maybe it's straight, maybe it's curved, maybe it goes like this. But something happens in between to connect them. That's an increasing graph. And on the other one, we're simply saying that at x1, we have a bigger value than we do at x2. And so likewise, we would be going downhill in some fashion between the two. That's a decreasing graph. You guys know what those are, though. I mean, if you saw them, you would know that's what they're talking about. However, it's important to realize and think about it from this perspective because it's going to give us some help on how to find these locations. So suppose that we have a continuous function. Okay, it's got to be continuous because we got jumps or disconnects in them. This is going to all fall apart real quickly. And we have a derivative that's positive. Remember, derivatives are just slopes. So I know you're writing, but I'm going to I promise I'll come back to the slide. Take a look back at this graphs over here. What can you tell me about the increasing graph in terms of the slopes? What are the slopes?
Positive.
They're positive, right? And what are the slopes in the decreasing graph? They're negative, and that is all this slide says. It says that if I have a positive slope, I have an increasing graph, and if I have a negative slope, I have a decreasing graph. That's all it says. Positive slope, increasing graph, negative slope, decreasing graph. We've already talked about that, right? We've made note of that. We've made awareness of that when we drew those graphs back in 3.1 or 3.2, wherever that was. We've talked through those ideas once before. So let's take a look at one more theorem. This is the first derivative test. There's a lot of writing on this one, so you guys have a lot of it already written down for you. Conditions first. It's continuous, and C is a critical number. Okay, critical number between A and B. All right, so this says that the derivative is positive between A and C, and this says that the derivative is negative between C and B. So I'm going to draw a picture of what's going on to make that actually make sense. First of all, this piece right here is telling me that A and B happen like this, and C's between them. So that's the first piece of information that's critical, important to what's going on. C is happening between A and B. So imagine this picture now. I'm going to move it so that I can draw a little bit more to it. Imagine this picture with what's happening here. This says that the slope is positive. What does it mean for the slope to be positive? It's increasing. So it's increasing between A and C. It's doing something like that, right? It's going uphill. And then it says between C and B, right, the next piece of the interval, the derivative is negative, which means the graph is decreasing. So what in the world must be happening at C? There's a maximum there. Because if your graph is increasing and then it's decreasing and it's continuous, right, it's actually connected, it would have to have a location at C where it's a maximum value. What's that?
Unless it's a sharp turn, though.
But we don't have a sharp turn because it said that it was, well, it's continuous. We could have a sharp turn and it would still be a maximum, actually. We don't necessarily have a derivative of 0 there, which is, I think, what you're thinking, Mandy. You're right. We don't know that we have a derivative of 0 there. But because it's continuous, we at least have a value there. Number 2 says the same thing, except in reverse, right? It says that instead of the graph being a derivative that's positive at first, it's going to have a derivative that's negative. So we've got the same picture going on. But between, oh, it didn't work quite right. Move it up a little bit. All right. Between A and C, right here, this says that the derivative is negative. So what does that mean in terms of my graph? It is decreasing. Not decreasing slope, but it's a decreasing graph, right? And the slope's negative, so the graph's decreasing. And then between C and B, over here, it says the derivative's positive, which means the graph is increasing. So what happens if you are decreasing and then you are increasing? You've got a local minimum. So this C right here is a local minimum. Up here it was a maximum. And if you've got a graph that has the same sign, that is, if it's positive and then it's positive, or it's negative and it's negative, that if it's positive and positive, it means it's increasing, something happens and then it's increasing again. Or it's decreasing, something happens and it's decreasing again. All it's telling you is that place where something happened is a place where we don't have a maximum minimum. And a really good example of that is that cube graph that I brought up a bit before. I don't have much space on the screen, but right? It is increasing here, it is increasing here, and it flattened out to 0 in between, but that means that location is simply not a max or a min. Nothing of this particular value is happening there. All right. So I want to do this real quick example because it's simple and it's easy and it shows exactly that what you expect to happen happens. Everything that we sort of described in that IE business over here, that we said, oh, look, it says IE, it changes from increasing to decreasing, that wasn't just sort of, fluffy language. It really works that way. This is a function that you're aware of. You know what this graph basically looks like. What's this graph basically look like? It's an upside down parabola, right? I mean, you guys know that. So if it's an upside down parabola, it means it has a local maximum because it's upside down, right? All right, so we're going to expect that happens. So it says first find the critical numbers and then classify them using the first derivative test. We haven't done that yet, but let's find the critical numbers. We've definitely done that. Critical numbers, last section in 3.2, we found out that we take a derivative and we set it equal to 0. So what's the derivative of this function? Good. And if we set it equal to 0, what do we get for x? 1. X equals 1 is either a local max, a local min, or intentionally it could be neither, but we're going to test it to see using the first derivative test. So how does it work? Well, it works like a number line. So we locate the value or values that we are going to test the critical numbers on the number line, and we test values before and after them. But we test nice values. I don't know about you, but 0 is a fantastic value. I love using 0 whenever I can because it's just everything goes away, right? And then maybe we test the number 2. If you don't test the same numbers as me, it doesn't matter. It won't change your answer. Okay, so you pick a number on either side, or let's say, for instance, we had critical numbers at 1 and 6. Well, if we had them at 1 and 6, we'd have to test 0, 2, and maybe 8 or something like that. I mean, we'd have to test more points. So you test whatever you have spacing apart on your interval. And where do you test them? Well, you test them in the derivative equation. So we use this to test. So we test f prime of 0, and we test f prime of 2. All right, so what is f prime of 0 going to actually equal? 4. What is f prime of 2 going to equal? -4. And we don't always get the same number, different signs. What is important about what we get is the sign. This sign, though it's not written, is positive. The second sign is negative. When a derivative is positive, what is a graph doing? Increasing. When the derivative is negative, the graph is decreasing. So visually over here on the graph, you just found out that this is increasing. And then it's decreasing. Which means what happens at x equal 1? It is a maximum. And you did it without the traditional algebra that you know, and that's great that you know it, but it confirmed that it worked, didn't it? I'm not saying it's easier or less easy, but I wanted to do a very clean, simple, easy example so you can see that it really does work with what you already know. So it says use it to test if it's a local max, min, or meter. So we have a local max at x equals 1. And all of the work that we just wrote down is how we classified it with that first derivative test. We evaluated the first derivative at locations found on a number line. Okay?